Hello friends, welcome to this new series on problems in physics for IIT JEE Advanced. So basically in this series my goal is to cover chapter wise, means class 11th and 12th all the chapters, problems in physics. So problems means advanced problems which contain some good concepts of physics. So advanced IIT JEE problems, that is the goal. So we are starting with the basic mathematics. So definitely basic maths also plays a very important role because physics, as you know, that calculus, errors, measurement. So with this also there are some good interesting questions. So we are starting with this. So in this video we will be covering the level 1 basic mathematics. Okay, so let's start. So let's start with question 1. So in this question, in an experiment, mileage of a car was measured to be 24 kilometer per liter of fuel consumed. So mileage of a car is given. After the experiment, it was found that 4% of the fuel used during the experiment was leaked through a small hole in the tank. Okay. Calculate the actual mileage of the car after the tank was repaired. So this is the question. So I want you pause this video and try it yourself before jumping into the solution. Okay, so I hope you got the solution. In case if you are you stuck somewhere, so let's look into the solution. So first let's try to understand what question is telling, then let's discuss its solution. So as per the question, in the question there was an experiment. In the experiment, the mileage of the car which was observed was 24 kilometer per liter, kmpl. So it is the observation in the experiment. So it is not the actual value. It is the value during the experiment, that is 24. And it is also given that during the experiment there was 4% error because during the experiment the car had a leakage, due to which 4% of the fuel got wasted, it got leaked out. So definitely the reading, that 24 reading, is the reading with 4% error. So it is very easy, we just have to calculate the actual mileage of the car. So let the actual mileage of the car be x kmpl. Since the experiment reading is 24 kmpl with 4% error, we can write that actual mileage, that is x, minus 4% of x is equal to 24. Because see, the experimental reading which we got 24, that is the reading with the leakage. So actual mileage minus 4% leakage is equal to the experimental reading. So x minus 4% of x is equal to 24. So with a very basic calculation you can calculate x, that is 25 kmpl. I hope you got the exact concept of the this problem, very easy problem. But still many of you might have struggled. So as you can see, physics is all about deep observation, understanding of question. Okay, so now let's jump into the second problem. A man is standing at a distance of 500-meter from a building. So there is a 500-meter tall building. A man is there is a tall building. Man is standing 500-meter apart from that building. He notes that angle of elevation of the top of the building is 3.6 degree. Find the height of the building. So we have to find the height of the building, neglect the height of the man, and take pi is equal to 3.14. So definitely I want you to pause this video and try it yourself before jumping into the solution. So I hope you got the solution, because it seems very easy problem. In case you had any difficulty, so let's decode the question and try to get the answer. So from the problem we can very easily see that there is a tower of height h, because height is unknown, but it is given that the distance of the man from the tower is 500. So in here in the triangle you can see that the h is the tower and 500 is the distance of the man, and angle of elevation. So you might be aware there are two concepts, angle of elevation and angle of depression. So whenever we look up to any object, so that gives angle of elevation, and whenever we look down to any object, that gives angle of depression. So here angle of elevation is 3.6 degree. So we just have to calculate the h. So from the diagram very easily we can calculate the h. So let's see how we can calculate. So the first concept here to be noted is that angle is in degree. So whenever we want to calculate any length, so we cannot calculate that using degree. We have to convert it into radians, that you know. So definitely converting degree into radian is very easy. You just have to multiply it by pi upon 180. So 3.6 into pi upon 180, you solve it, you will get the angle in radians. So it is 0.0628 radians. Okay. Now you know one formula, that theta is equal to arc upon radius. So theta we can also consider as angular displacement. So theta is arc upon radius, that you know. So we just have to calculate the arc, or to be more precise, tan theta is perpendicular upon base. So tan theta is h upon 500. So here h will be 500 tan theta, since angle is very small, because that 0 point, so we can write tan theta into theta, approximate, because we are looking for an approximate answer. So in objective type, you might be aware ki you get a idea, because there will be four options. So you get an idea ki, okay, your answer is around 31. So you can just directly tick. So you just have to put the values and you will get the answer 31.4 meter. I hope now that problem was clear. So now let's jump into third problem. Okay. So third problem says that a smuggler in a Hindi film is running with a bag. So the dimension of the bag is given, 0.3 meter into 0.2 meter into 0.2 meter dimension. Okay. So there is a typo, that means should be meter. Okay. Meter in dimension. The bag is supposed to be filled with gold. So he has got a bag of a particular dimension, and he is a smuggler. So definitely he will be doing smuggling of gold. So he will be filling the gold. Do you think that the director of the film made a technical mistake here? Density of the gold is 19.6 gram per cubic centimeter, cc. Okay, cc means cubic centimeter, yeah, centimeter cube, because volume, you know that, density, mass upon volume. So here in this question, this is a basic conceptual question, understanding. So I want ki you just first try it out by yourself before jumping into the solution. Okay. So I hope you come up with a very valid answer for this. So let's try to decode the question and get into the solution. So here it is dimension is given. So the dimension is n into b into h. So it is a cube, because bag we can consider a cube. So from the dimension we can easily calculate the volume. So we have the volume of the bag, and we have to fill the bag with the gold. So density of gold is given, and the volume we have. So definitely from these two parameters we can calculate the mass. Because see, in this question we have two parameters, we have the volume, we have the density. So definitely we should try to calculate the mass. So one very interesting, very important thing to be noted here is this: see, density is gram per centimeter cube, volume is in centimeter cube, but the dimension is in meter. So definitely, if you directly solve and put the formula, you will get a wrong answer. So this I think you might be aware, and you should be very careful with the units. So what I have done, I have converted the meter into centimeter. Then I calculated the volume. So as you can see, volume we got 30 into 20 into 20. So that is 12,000 centimeter cube. Now we have the volume, we know the density, so we calculated the mass, so volume into density, so it was 235.2 kg. So from the observation, we can say that mass is huge because 235 kg, even weightless, that what you can say that weightlifters, they also struggle in carry such a mass. So how can a gold smuggler be? So definitely there is a technical glitch made by the director of the movie because carrying such a mass is infeasible. Okay. I hope you got the main observation. So two things we noted. One is that whatever data is given, we should work with that. And second is the unit. Unit plays a very important role. Yeah. So now let's jump into the next question. That is question 4. I hope you are enjoying. Physics is very easy. The idea is that just you have to solve lots and lots of problem and feel it. So it will be very interesting. Okay. So now here in this question, a particle moves along the curve. So see every equation, every linear equation represents a straight line. Every quadratic equation represents a curve, or any polynomial represents a curve. So 2-degree equation is a parabola, 3-degree equation will be having some slopes. So this you might be knowing. So definitely here equation, a polynomial is given. So it is containing two variables y and x because it is an xy plane. So it is representing a curve. So curve, we can say that it is a path. Okay, so a particle is moving along this path. Find the points on the curve at which y coordinate is changing 8 times as fast as the x coordinate. Okay, so you have to find that special points on the curve where change in y coordinate is 8 times as fast as change in x coordinate. It means that at that point, if we change x by 1 unit, y will be changed by 8 units. So very interesting problem. So I want you to struggle with it, fight with it, and come up with a solution. So pause the video and try it yourself before jumping into the solution. Best of luck. So I hope you got the solution. And if you faced any problem, so let's look into the solution because it seems very interesting. So see, whenever we talk about change, definitely we have to apply calculus. Calculus is the study of change because function in itself is representing a dependent variable and an independent variable. How uh, an independent variable is changing the dependent variable. So here the equation is given and dy by dx is given because change of y with respect to x is 8 at some particular point. So what you can do, you can just calculate the dy by dx of this equation. So that is 3x square upon 6. I hope you are well aware of this differentiation, very basic differentiation. So 3x square by 6 and it should be equal to 8 as per the problem. So you will get the points. So at those points, at those x coordinates, we have dy by dx is equal to 8. And now putting the value of x in this equation, 6y is equal to x cube plus 3, you will get y. So y is 11 upon 11 comma minus 31 upon 3. So you get the point, that is minus 4 minus 31 3 and 4 comma 11. So these two are points. So okay, so now let's jump into next problem. Okay, so next problem, as you can see, the area of a regular octagon of side length A is A. So we have an octagon, you know, 8-sided figure. So each side is of length A and the area is capital A. Okay, so we have to find the time rate of change of area of the octagon if its side length is being increased at a constant rate of beta meter per second. Okay, so from the question you can see that the side length is increasing every second because if we talk about rate means time. So beta meter per second, so every second the length is increased by beta units. So in the problem we have an octagon, and beta meter per second, every side is getting increased, so octagon is getting increased. Okay, so we have to find the change of area per unit time. So definitely when octagon will increase, its area will also increase. So you have to find the rate of change of area with respect to time. So very means it is relatable. I hope you can get a feel, getting you are getting an idea ki how you can solve it. So you have to find the rate of increase of area, rate of change of area. Okay, so and one more thing in the A part is the time rate of change of area, which you will calculate, is constant or it is dependent on some quantity. So that also you have to find out, is it a constant or not. And the B part, find the approximate change in area of the octagon as the side length is increased from 2 meter to 2.001 meter. It is a very easy question. So it is telling ki if the side length is increased from 2 meter to 2.001 meter, definitely area will increase. So what will be the change in area? That you have to calculate. So I hope you can very easily do that. So definitely before jumping into the solution, let's do it. Let's crack this problem. So pause the video and try it yourself before jumping into the solution. Okay, I hope you are done with the problem. So let's look into it. So first, definitely you should be aware of the area of the octagon. So area of triangle you might know, area of rectangle you might know, four-sided figure, L into B. See, area of octagon calculating is very easy. You just have to draw the octagon and you have to identify that rectangle, triangle, and you have to sum it up and finally calculate the area. Because octagon, when you will calculate the area, you will get many small, small triangles and rectangles. So you have to sum it up because it is a symmetrical figure. So you will get the area to 1 plus root 2 a square. So this you have to prove by yourself. Definitely it will be very helpful for you. So find the area. So once you have the area, you have to calculate the rate of change of, whenever we talk about rate, it is change of any quantity with respect to time. So here we have to calculate the rate of change of area. So change of area with respect to time. So dA by dt you have to do. So in the equation dA by dt you can very easily do. You will get 4 root 2 plus 1 a dA by dt. So this is very easy. And dA by dt is given that d small a is the side, because it is given ki side is changing per second with beta unit. So small dA by dt you can substitute it with beta. So you get the answer. So this is the answer. So see, one step answer, 4 root 2 plus 1 a beta. So see, in competitive exam, this is the beauty of the competitive exam. Any problem, whether it is a very difficult problem, it will be solved in a very limited time. If you are taking lots of time, you stop and reiterate your strategy because you are doing mistake. If you are taking lots of time, then definitely you have taken yourself into the wrong path. Okay, yeah. So we have calculated this time rate of change. Now the next thing is this time rate of change of area is constant? So here, see, looking into the equation that 4 root 2 plus 1 a beta, we can see that 4 root 2 plus 1 is constant because it is not changing, it is constant. Sorry, a is constant, but beta, uh, beta is constant. Sorry, beta is constant, but a is not constant because in the problem it is given that side is changing continuously. So here many students do mistake. So they tick that it is a constant, but it is not a constant because in the problem it is given that a is increasing. So how can it be a constant? So definitely this expression is not a constant because it depends on side length, which itself is dependent on time. It is increasing with time. Okay, I hope you got the solution. And okay, so now let's move to the next B part. So B part is very easy. As you can see, When the length is increased from 2 to 2.001 meter, you have to calculate the area. So you can do it in multiple ways. So the traditional method will be to calculate the formula. You take a1, a2, then a2 minus a1, simplify the formula, then put the value, you get the answer. That is a traditional method. But let's do a very fast method, because the traditional method requires some calculation. The fast method is, you have this area, you just do dA by small dA, means change of area with respect to change of side. It is very understandable, because when side changes, area changes. So we are calculating the change of area with respect to change of side. That is also only we are calculating dA by d capital A, that is area upon d small a, that is side. So that with a very basic differentiation, you get 4 root 2 plus 1a. Okay. Now, ultimately, we have to calculate delta A, because delta A is the change in area. See, there is a difference between delta A and dA. So delta A is a change in a significant time, measurable time, and dA is instantaneous change, means a very infinitesimally small time. So definitely we have to calculate delta A. So delta A, we can write dA upon small dA into delta A, delta small a, as you can see here. Okay. So that we can write. So d capital A upon d small a we have already calculated, and delta A we know. Delta A is change in that side. So that is 2.001 minus 2.01, sorry, minus 2.0. So you just multiply and you get the answer. So answer is 0.0019 meter square. Okay. Hello friends. So welcome to the second video on the series, that is problems in physics for IIT JEE Advanced. So we already have covered one video on basic maths level 1. So definitely we will today we will be covering basic maths level 2. So it will be a bit more advanced problems as compared to the previous lecture which we covered, that is level 1. Okay, so let's jump into the problems. Okay, first problem. So, spirit in a ball evaporates at a rate that is proportional to the surface area of the liquid. So, there is a ball. In the ball, there is a spirit. Spirit is a special type of liquid, you know. So, it evaporates. And definitely, the rate of evaporation is directly proportional to the surface area of the liquid. It is understood because you can very easily observe, imagine, if you have a small ball and you have a large ball, in let us suppose in 10 seconds, if you observe, you will see that the amount of liquid which evaporate from the larger bowl, the amount of liquid which will evaporate will be more, because uh, if the bowl is larger surface area is exposed to the surrounding, and hence more particles will be emitted. So the rate of evaporation is directly proportional to the surface area of the liquid. It is given in the question and it is understood also. Yeah. It is also given that initially the height of the liquid in the bowl is h naught. Okay. And it becomes h naught by 2 in time t naught. So in any time t naught, the height becomes h naught by 2. It is obvious because liquid is evaporating, so height will decrease. Now they are asking how much more time will be needed for the height of liquid to become h naught by 4. So apart from t naught, see at time t naught, height is h naught by 2. Now they are asking at what time the height will become h naught by 4. So at what, how much more time? So they are asking more time. So there is a trick here. Okay. So first I want you try it yourself. Pause the video and try it yourself before jumping into the solution. Yeah. Okay. So I hope you are done with the you came up with the solution. So let's see. So as we have already seen the problem is very straightforward. It is clear to us. There is a ball. Initially the height is h naught at time t naught, and after some time, definitely liquid is evaporating. So after some time, the height will decrease. So they are asking at what time that height will be h naught by 4. Okay. So if you look into this diagram, the ball, so from it you can very easily see that let the area of cross section of the ball at height h be capital A. Because see, the beauty is this key in the ball at different height area will be different. Because see, as we are as the liquid is decreasing, its area is also getting reduced, and hence rate of evaporation is also getting affected. So a very nice observation we can see from this diagram. Key in the ball, as the height is decreasing because liquid is evaporating, so area is also decreasing. So let us suppose at any height h area be capital A. Okay. Now let us do the observation for a very small time instance, that is dt. So for very small time instance dt, if we look into the ball, we will see that a very small evaporation will take place. So the change in height will be dh, means height will decrease by dh. And you know that volume is equal to area into length or area into height. This you should know. So definitely volume of liquid that evaporates at time interval dt, that will be the area, that is capital A, and height which gets evaporated, that is dh. So AdH. Okay. Now in the question, and as per our concept also, we already know that rate of evaporation is directly proportional to the surface area. So what is rate of evaporation? Volume of liquid evaporating per unit time. So volume of liquid evaporating is AdH, and here per unit time is dt. So AdH upon dt is directly proportional to A, because A is the area of cross section which we have taken. I hope it is clear. Until now everything is very clear, I hope. Now, definitely, if we have to remove this proportionality constant, directly proportional, so we have to introduce a proportionality constant. So let us, we are introducing minus k. So here we are introducing minus because, see, h is decreasing with time. So dh by dt will be a negative quantity. See, what is dh by dt? Rate of change of height with respect to time. So with time height is decreasing, so dh by dt will be a negative quantity. This you know, basic calculus. If any quantity increases with time, it is a positive. If any quantity decreases with time, it is negative. So dh by dt will be a negative. So that's why we are introducing a minus sign here, in the proportionality. So we can write a dh by dt is equal to minus k upon a. Here a we can cut. So definitely we get dh is equal to minus k dt. A very straightforward calculation. Now you have to just do the basic integration. So we will be integrating dh from, see, integration always we do from any initial boundary condition to any final boundary condition. So here we are doing integration from h naught, that is the initial height, to any height h. Okay. And time is 0 to t. Okay. So when you do that, so you will get the relation. So this is the very most important relation for this question. So this is small h is equal to capital H naught minus kt. So small h is the height of the liquid at any time small t. So by changing the value of t, you can calculate height, and here k is unknown. So still our equation is not complete because k is unknown. So we have to calculate k, and fortunately in the question we have given one condition using which we can very easily calculate k, because in the question it is given that when time is t naught, height is h naught by 2. So putting that t is equal to t naught and small h is equal to h naught by 2, you can very easily get k. So the k will be h naught upon 2 t naught. Okay. Yeah, so you can very easily look into it. Now we got the K. Now the equation is complete. Question they are asking ki how much more time will be needed for the liquid to become H naught by 4. So we have to calculate the time. Uh, First we have to calculate the time when the liquid will be H naught by 4. Then there is one more step. So that is the most important step that I will tell you. So let the time be t. So instead of small h, we will write h naught by 4. So h naught by 4 is equal to h naught minus kt. So small t we get 3 by 2 t naught. Now this is not the answer, because in the question they are asking how much more time. So more time means from we have to measure not from t is equal to 0 but from t is equal to t naught. So this is the trick in this question, because you have done such a hard work and you came up until here, and it might be there in the objective this option is also there. So you got excited, oh aa gaya, I got the answer, I got the answer, and you tick, and after that you realize, oh, it became wrong. So how much more time? So more time means you have to measure from T naught. So sorry, 3 by 2 T naught minus T naught you have to do, because we are measuring not from T is equal to 0 but T is equal to T naught. And we know that at t is equal to 3 by 2 t naught, the height is h naught by 4. So if we minus 3 by 2 t naught minus 2 t naught, we get the how much more, which the question is asking, and that how much more is t naught by 2. So this is the answer, t naught by 2. Wonderful. So I hope this is clear. So now let's jump into the second problem. So in the second problem, show that the volume of a segment of height h of a sphere of radius r is given by this relation. So very straightforward. We have a sphere, okay, sphere, and they are telling ki in the sphere we are taking any segment with height h, as you can see in the diagram. So the shaded segment of height h, we have to calculate its volume. So ultimately the goal is to calculate its volume. So in the question is to just compute this value. They have already given the value and you have to prove it. So definitely it is a very important question, because in problems definitely they will directly not ask you to prove, but in the problem there might be many scenarios in which you have to get to this point to get to the final answer. So that's why I have included this question. So please do it. Please pause the video and try it yourself before jumping into the solution. Okay, so I hope you came up with the solution. So let's see. So consider a disk shape element of thickness dx at a distance x from the center. So definitely we have a sphere. From the distance x, we take a disk shape element of thickness dx, and uh, we have the radius capital R, and let us suppose the distance from that we draw a perpendicular, that is x, and we get small r. So here we have a right angle triangle. So using Pythagoras theorem, we can very easily calculate small r. Okay, very easy. So small r square will be equal to capital R square minus x square. Okay. Now the disk. See what disk is representing here. If you talk about sphere, so sphere is a 3D figure. So definitely you can feel that it is made up of many disks. So let us suppose you have plates. So you just pile up lots of plates. So you get a sphere-like structure. So sphere is made up of disk. So we have taken any particular disk of thickness dx. So disk is that disk. Okay. Now if I talk about the volume of disk, so as I have already told you, ki, volume is equal to area into height or area into length. So area of disk because disk is a circle, so area will be pi r square. Very it is understood. Okay. And the height is dx, as you can, so the area will be pi r square dx. So here r is the radius of the disk. R is the radius of the disk. Okay. So we got the volume of the disk, and instead of r square, we can put that capital R square minus x square. Okay, because see here we cannot use small r because small r is unknown. In the question we are given the radius of the sphere, but we have not given the radius of the disk, because disk can be any disk. So every disk will have a different radius, so we have to eliminate that r. So that's why we eliminated that r and substitute it with r square minus x square. Okay, nice. So now we have the dv. So definitely integrating dv, because integration, it is summation. So we have this we have calculated the volume of the small segment. Now if we do the integration, we get the volume of the entire segment of the sphere. So we do the integration from x, because we have to just calculate the volume of the segment, not the entire sphere. So that's why we will be doing integration within that boundaries only. So that is r minus h, because r is the entire radius, as you can see, r. So r minus h, from r minus h to r. Okay, so from r minus h to r, you can very easily see that it represents the segment which we are looking for. So you do the integration. So instead of dv, you can put that pi r square minus x square dx, and it is a very basic integration. So you can go through it, and you just solve it, and once you solve it, you get the answer. So answer will be the same which is there in the question. I hope this problem is clear. Okay, friends, so let's jump into the third problem. So third problem seems to be very big one. So it is into three parts, so let's decode it one by one. So the amount of energy a car expends against a resistance is approximately given by capital E is equal to capital A, capital A, capital D, V square. So here E is the energy measured in joules, K is a constant, capital A is the cross-sectional area of the car viewed from the front. Okay. D is the capital D is the distance traveled by the car in meters, and small v is the speed of the car in meter per second. Okay, so we have given some basic parameters about the car, and it is also given that when the car moves, definitely it moves against the air resistance. So whenever we do work against any opposing force, there is a loss of energy. So definitely car means expense means loses some energy. Okay. Now Julie. Okay, so Julie wants to drive from Mumbai to Delhi and get good fuel mileage. So the goal of Julie is to get the good fuel mileage. For the following questions, assume that the energy loss is solely due to air resistance. So we have to neglect the heat, because see, energy is lost in heat also, due to friction of road also. We have to neglect all that. We just have to consider that energy loss is taking place only due to air resistance. This is given in the question. Now three things you have to, three parts are there. So let's look into it. Julie usually drives at a speed of 52 to 54 kilometer per hour. Okay. How much more energy will she use if she drives 20% faster? Very straightforward question. See, if she increases her speed, so definitely more energy will be expended. So how much more energy will be expended? How much more energy will be lost? That you have to calculate. In the B part, there is one more character in this question, that is Harshit. Harshit drives a very large SUV car, and Julie drives a small car. Every linear dimension of Harshit's car is double that of Julie's car, because you know SUV is a very big car and Julie's car is a small car, so every linear dimension will be double. It is given in the question. Find the ratio of energy spent by Harshit car to Julie's car. So big car to small car, energy ratio you have to calculate when they cover the same distance, and also speed of Harshit was 10% faster. So big car, SUV car was moving with 10% faster speed. They both the car covered the same distance. So you definitely, so during the journey, both the car will be losing some energy. So you have to calculate the ratio, key ratio between loss of energy by the Harshit's car, that is the SUV car, and the small car. So it is also very straightforward question. Uh, okay, so C part, they are asking, write the dimensional formula for K. That is capital K. In the equation, capital K is given, so you have to calculate, find the dimensional formula for K. Will you believe that K depends on density of air? Okay, so definitely pause the video and try it yourself before jumping into the solution. So let's jump into the A part of the problem. So the question is very clear. So if we look into the A part, so in A part it is given that if Julie drives the car 20% faster, then how much more energy the car will use? Yeah, how much more energy will be wasted by the car? So this is what we have to find. Okay, so we can very easily see that E is equal to KAdV square, it is given. So let us suppose if Julie is driving with a speed of 54 kilometer per hour, then the energy loss, yeah, energy expended against a resistance, let it be capital E. So what we can do, we can write capital E is equal to, instead of V we substitute it with 54. So 54 into 54 into KAD. So this is E. Now if the speed is 20% faster, so 20% faster means 54 plus 20% of 54. I hope it is clear. So definitely now the velocity will become 54 plus 20% of 54, and if we put this velocity we get E1. So E1 is the loss in energy at high speed, so that is E1. So we when we substitute the values, so we get E1 is equal to 54 into 6 by 5 into 6 by 5 into KAD. So this very easily you can get by a simple mathematics. Okay, so now we have now we have E1. So what, so see in the E1, instead of KAD we can substitute it with E upon 54 into 54, because this is also very clear. So we get a relationship between E1 and E. So after solving we get E1 is equal to 36 upon 25 into E. So I hope until here it is very clear. Okay, now what exactly we have to find? How much more energy? So here also we have to calculate the rise in energy, means how much more energy it will be wasted when the speed is increased. So it is very straightforward. Final energy minus initial energy upon initial energy into 100%. So E1 minus E upon E into 100%, that we have to calculate, because how much more energy it is asking. So more energy means difference in energy, rise in energy. So rise in delta E, so that is E1 minus E upon original energy, that is E into 100. So after solving you get the answer to be 44%. Now let's jump into the B part. Okay, so B part is also very straightforward. So in the B part, as you can recall, there is a big car, there is a small car, SUV, and normal small car, which Julie is using. So we can consider area of cross section of car to be as area of rectangle, because we can imagine car to be a kind of a rectangle if we look from the front, and area of rectangle, you know, L into B. Yeah. Now let us suppose the area of cross section of small car be A2. Means for the small car, all the things we take 2 means A2, V2, and definitely area of cross section for a large car is A1. Now since linear dimension is double for the large car, so A1 will be equal to 4A2, because if it take length to if the length of small car is L and breadth is B, so for the large car it will become 2L and 2B. So if we multiply, we get 4LB. So LB is the A2. So ultimately the trick is in this concept. So area of cross section of large car is that 4A2. So A1 is equal to 4A2. Very straightforward. Yeah. So now the speed of large car V1. So sorry, in the problem it is given that the large car is at 10% faster than the small car. So speed of large car V1 is equal to speed of small car V2 plus 10% of V2. So when you will solve it, you get V1 is equal to 11 by 10 V2. Very straightforward calculation. So now you have to calculate E1 by E2, because ratio you have to calculate. So as you can see, E1 by E2 by the formula, it will be K A1 capital D V1 square upon K capital A2 D V2 square. So now here A1, as we have already derived, A1 will become 4A2, and V1 is 11 by 10 V2, so 11 by 2 V2 square, and the denominator will be as it is. We will do some cuttings. After cuttings and all that, we get the ratio to be 121 upon 25, and we get the final answer 4.84. So this is the answer. Okay, so the C part. So in the C part, they are asking write the dimensional formula for K. So definitely, if you have to write the dimensional formula for K, so K will be equal to E upon AdV square. So E is energy. So you know the dimension of energy. So energy is equivalent to work. If you talk about dimension, what is work? Work is force into displacement. So what is the dimension of force? Force is mass into acceleration. So m L t minus 2 into the displacement is L. So ultimately the dimension of energy is ml square t minus 2. Area, you know, L square. D is the distance, that is L, and V. What is V? V is velocity. So velocity is displacement upon time. So L t minus 1. So if you square it, you get L square t minus 2. So after all the cuttings and all, you get the dimension to be ml minus 3. Very easy. So this is the dimensional formula for K. Now one more thing they are asking ki, whether K depends on density of air or not. Okay. So if we look into the dimension carefully, you can see that it is like mass upon volume, because the volume is L cube. So definitely it is dependent on density, because the dimension itself is of density. So the answer is yes. Yes, it is dependent on density of air. So now let's jump into the fourth problem. Okay. The volume flow rate Q in meter cube per second. So that is cube meter cube per second of a liquid through pipe having diameter d is related to viscosity of water. The unit is in Pascal second, and the pressure gradient along the pipe, that is dp by dx, and they have given the concept of pressure gradient also, and they have given a formula. So let's understand the question. So see, in the question there is a pipe. The pipe diameter of pipe is d, and definitely in the pipe liquid is flowing. So the viscosity of the liquid is given. Now definitely when liquid flows, there will be a rate. So rate is Q. So what is rate? Rate is volume of liquid flowing per second. Every second how much volume flowing, that is the rate of flow. So rate of flow is given Q. Okay, per second how much volume is flowing. We know the viscosity of the liquid. that special symbol of viscosity, and we know the diameter of the pipe. All these parameters are given. And one more very interesting thing, pressure gradient. So what is pressure gradient? Pressure gradient is the change of pressure with respect to length. Yeah, rate of change of pressure per unit length along the pipe. So the pipe is not uniform. If this is a special pipe where pressure changes as we move along, so that that change in pressure is measured with dp by dx, that is pressure gradient, rate of change of pressure per unit length along the pipe. So as you move along the pipe, pressure changes, so dp pi. So it is a non-uniform pipe, it is given, and the formula is given. Now and k is dimensionless constant. So what you have to do, you have to find abc. So I hope the problem is very clear. So yeah, find abc. So pause the video and try it yourself before jumping into the solution. Okay, so I hope you are done with the problem. So let's decode. So problem is very clear. We have the equation. So let's directly dive into the equation. So see, whenever we have to calculate this ABC, so we have to convert all the units into dimensions, because these units are not standard units. These are all derived units. So first we have to convert it into dimension. So let's start with the viscosity. So viscosity in the question itself it is given, but you should also remember it is Pascal second unit. So Pascal, you know what is Pascal? So Pascal definitely you should know. So it is force upon area into second. So Pascal is force upon area into second. So force dimension you already know. Area is L square, force is mLT minus 2, and second is T1. So when you solve it, you get the dimension of viscosity, that is mL minus 1 T1. Now similarly for D is the diameter. So diameter is length, L1 is the dimension, very easy. dp by dx, very interesting. So dp by dx is what is p? Pressure. Pressure is force upon area. So force upon area into 1 by l. Yeah, because it is p by x. X is l because length. So f by a into 1 by l. So f you know a, and after solving you get that dimension of dp by dx also. Now here what you do, and uh, sorry, if you talk about capital Q, so capital Q dimension you can very easily get because capital Q is the rate of flow, and unit it is given meter cube per second. So meter cube is L cube T minus 1. So L cube T minus 1 is equal to this. So you substitute, and you bring mass together, L together and T together, and you compare it with I think this concept is clear, very basic concept. So with this you will get that a plus c will be 0, minus a plus b minus 2c will be 3, minus a minus 2c will be minus 1. Okay, and with this you get the answer that a is minus 1, b is 4, and c is 1. So this is what you have to find. Okay, so let's jump into the sorry, fifth problem. The potential energy U of a particle can be expressed in certain case as capital U is equal to capital A square upon 2m r square minus capital B m m upon r, where small m and capital M are mass and r is distance. Okay. Find the dimensional formula for constants. So in this equation, capital A and capital B are constant, capital M and small m are mass, it is given, and small r is the distance. So it is a very easy question. So just pause the video and try it yourself before jumping into the solution. Okay, so I hope you have done the problem. So see, if I talk about u, U is potential energy. So what is the dimension of energy? It will be the dimension of work. So work is force into displacement. So dimension of work is ml square t minus 2. Okay. So we got the dimension of energy. Now you know that if we talk about principles of dimension, so in any equation, if you have addition, subtraction, so all the independent terms dimension should be equal. It means dimension of a square upon 2 m r square should be equal to dimension of u. So using this concept, we can get to the solution. So what we can do, we can assume the dimension of A to be MA, LB, TC, because we don't know, so we are taking ABC as unknown. Now, sorry, using that the principle which I told you just now, we can write ML square T minus 2 is equal to M2 minus 1. See, now what you do, instead of that a square, you will substitute, instead of a, you will substitute ma lb tc. So it becomes m2a l2b t2c upon m l square. So when you solve, you get this m2a minus 1 l2b minus 2 t2c. So you just compare it. So 2a minus 1 is equal to 1, 2b minus 2 is equal to 2, 2c is equal to minus 2, or a, b, c you get. So a is 1, b is 2, c is minus 1. So you just substitute that, so you get the answer. So the answer is for the capital A dimensional formula is ml square t minus 2. Okay. Similarly, let dimensional formula be for b m a l b t c. Yeah. So similarly, we have to just equate. So for energy we know, and for this we have calculated that this B, we have assumed MALBTC and mass MN upon L. So when you do the solving and comparing, you get A minus 1, B 3, C minus 2, and you put and you get the answer. So it was a easy question. So I hope you got the concept. Okay, so let's look into problem number 6. So the maximum height of a mountain on earth is limited by the rock flowing under the enormous weight above it. So definitely, if we talk about mountain, so definitely mountain is a huge structure. So the bottom of the mountain, it always experiences heavy pressure due to the mass above it. So because of that, it starts breaking down. So the maximum height of a mountain is limited by the breakdown of its bottom surface. So it is understood, we can very easily observe it. Studies show that maximum height of the mountain depends on Young's modulus Y, acceleration due to gravity G, and density of rock D. Okay, it is given. So A part, write an equation showing the dependence of maximum height of mountain on Y, G and D. It is given that unit of Y is Newton per meter square. Very nice. So it is a very good question. So you have to write the formula for H. So you have to derive the formula for H using the principle concept of dimensions. And the B part is, take D is equal to 3 into 10 to the power of 3 kilogram per meter cube. Y is equal to 1 into 10 to the power of 10 Newton per meter square, and G is equal to 10 meter per second square. Okay, this we can take, it is given. And assume that maximum height of a mountain on the surface of earth is limited to 10 kilometer. So height of Mount Everest is nearly 8 kilometers. Okay. So in the question it is given that we can assume the maximum height to be 10 kilometer. So Mount Everest, you know, it is the tallest mountain. So its height is 8 kilometer. Okay. So write the formula for H. So in the B part, you have to write the formula for H, and in the A part, you have to establish the dependence of H on all the given parameters. So it is a very straightforward question. So please pause the video and try it yourself before jumping into the solution. Okay. So I hope you have done the problem. So let's jump into the solution. So if we talk about the A part, so definitely in the question itself, it is given that H is dependent on Y, G, and D. So what we can do, we can write H is proportional to Y की power of A, G की power of B, and D to the power of C. So this we can assume because exactly we don't know how they are dependent. So we can write YA, GB, DC as you can see. And when we remove that directly proportional, we introduce a proportionality constant. So initially we start with this equation: H is equal to K capital YA GB DC. Okay. Now we know that from the principles of dimensions, dimensions of LHS should be equal to dimensions of RHS. So this you know. So if I talk about the dimension of LHS, that is the dimension of height. So height is L. So definitely its dimension will be M0 L1 T0. It's very clear. And if I talk about dimension of RHS, so first I have to calculate the dimension of Y. So how you will calculate the dimension of Y? Using the unit. So in the question the unit is given. Unit is Newton per meter square. So Newton per meter. So what is Newton? Newton is force. Force is mass into acceleration. So mlt minus 2. So mlt minus 2 into L minus 2. So the dimension of Y is m L minus 1 T minus 2 की power of A. Similarly, gravity. What is gravity? Gravity is acceleration due to gravity. So it is acceleration. What is acceleration? Change in velocity per unit time. So what is velocity? Lt minus 1 upon T. So it is Lt minus 2. So the dimension of G is Lt minus 2 to the power of B. Similarly, D. What is D? D is the density. Density is mass upon volume. So ml minus 3 because volume is L3. So m1 L minus 3 is the dimension of density. So ml 3 ml minus 3 to the power of C. So in this way we derive the dimension of every quantity. Now what you do, you just solve it. How you will solve it? You just group all the m together, l together, a together and compare the powers. So definitely we get a plus c is equal to 0. When you solve, you will get this: minus a plus b minus 3c is equal to 1, and minus 2a minus 2b is equal to 0. This you get. Solving it, you can very easily get a is equal to 1, b is equal to minus 1, c is equal to minus 1, and putting the value, you get the formula. H is equal to k y upon gd. So see how magical it is. So using the principles of dimension, we establish the relation of maximum height of a mountain on the given parameters. So yeah, so I hope it is clear. And see, looking into the dependency, you can see that it is still incomplete because k is unknown. K is a constant, so we have to calculate the value of k. So once you calculate the value of the k, then it is 100% complete. But in the question it is asking for dependence. So from the dependency point of view, uh, we got the answer. Yeah, so now let's jump into the B part. So in the B part, it is given that the density is given, Y is given, and G is given, and also they are telling ki H we can take 10. So definitely putting all the values, we get K. K is the unknown. So once you know get the K, then you get the exact formula. So by solving, you get the K to be 0.03. Okay, here height is in kilometers, so that's why we are writing 10 into 10 to the power of 3. We are converting it into the meter. So you get K. Now the final formula for H is equal to 0.03 Y upon GD. So this is the final formula. So unknown we have calculated. Yeah. So I hope this problem is clear. So it was a very interesting problem. So now let's jump into the next problem. Yeah. So problem number 7. So a particle of mass m is given an initial speed v0. It experiences a retarding force that is proportional to the speed of the particle. F is equal to AV. So A is a constant. Small a. So definitely a very straightforward observation. We have a particle of mass m. It is moving with an initial speed v0, yeah, v naught. So in the problem it is given that the retarding force acting on the particle is directly proportional to the velocity. So if the particle moves faster, the retarding force will also increase. And if the particle slows down, the retarding force also decreases. So it is given. So you have to calculate two things. First is the write the dimensional formula of constant A, and the second B part is using dimensional analysis derive a formula for stopping time of the particle. Okay, so what is the stopping time of the particle? So see, you know that if the particle is moving, it is experiencing a retarding force as given in the question. So if any object is experiencing a retarding force, after some point of time, it will stop. It is a very straightforward observation. So stopping time is the time at which the particle will stop. So that is the stopping time. So you have to derive the formula for stopping time. Very interesting. And then you have to also do some observation like, does your formula tell you how t depends on initial speed v naught? What can you predict about the constants obtained in the formula? Yeah, so I want you to try this solution. So try this problem and get the solution. So please pause the video and try it yourself before jumping into the solution. Okay, so I hope you are done with the solution. So now let's look into it. So see, we it is given in the problem f is equal to av. F is equal to av is given. Okay. So what A will become F upon V. So what is the dimension of F? You all already know F is mass into acceleration. So mLt minus 2. And what is V? V is displacement upon time. So LT minus 1. So after all the cutting, you get the dimension. So dimension we have calculated. Okay, so let's jump into the B part. So in the B part, definitely first we have to derive the formula for the stopping time. So looking into the problem, definitely time is not given anywhere. So we know that initial velocity is given v naught, and one relation is given f is equal to av. F is equal to av, it is given. Okay. So now what we can do? What is force? Force is mass into acceleration. And what is acceleration? Acceleration is change in velocity upon time. So ultimately, if we look into the quantities, so what quantities we have? We have mass, we have velocity, and we have time, and we have a constant A. So all these quantities we have. So what we can do? We can write T is definitely, we can assume that stopping time depends on all these quantities. So we can write T is equal to K. K is a proportionality constant. So K and AX, MY and V0 Z. Okay. So this we can assume. So ultimately we are assuming that the stopping time is dependent on your A, that is the constant, the mass, and the this velocity. Okay. Now what you have to do, these types of problem we have already done. We just have to compare the dimensions of both LHS and RHS. So if I talk about the LHS is time. So what is the dimension? M0 L0 T1. Understood? And if I talk about the right hand side, so the dimension of A we just computed, that is mt minus 1. So mt minus 1 to the power of x. And what is m? M is mass. So m to the power of y, capital M to the power of y. And v naught. What is v naught? It is velocity. So velocity is displacement upon time. So it is lt minus 1. So lt minus 1 to the power of z. Now you group mass, length, and time together and compare the powers. So definitely after solving, you get x is equal to minus 1, y is equal to 1, and z is equal to 0. A very straightforward calculation. And putting the values, you get t is equal to k m upon a. So see, uh, how we have derived the formula for stopping time. So stopping time, the time at which the particle will stop because particle is experiencing a retarding force. So stopping time is equal to k. K is a constant, m upon a. So here a is also a constant which is given in the problem, and m is the mass. So interestingly, if you do in-depth observation, so you find that t should be dependent on v. It is a very basic observation. For example, see, we know that if a particle is moving faster, it will experience more retarding force. More retarding force means it will stop early, and if the particle is moving slowly, it will experience less retarding force. If it is experiencing less retarding force, then definitely it will stop after some time. It will the stopping time will be larger. So ultimately, stopping time should depend on v. Stopping time should depend on, but in this derivation derived from the dimensional analysis, v is not there. So this can be possible only if k is infinity. Means this is possible only at infinite time, because uh, in a normal situation it is not possible, because t is directly dependent on velocity, as we can very easily observe. Yeah, so this is the solution. Okay, so I hope you got the concept. So now let's jump into the next problem. Okay, so problem number 8. See, assume that maximum mass m1 of a boulder swept along by a river depends on the speed v of the river, acceleration due to gravity g, and density d of the boulder. So what is this boulder? Boulder, you can assume a very big stone, because see, in the river there are big stones that also flow with the flow of the river. So boulder, you can assume a big stone. So we have a big stone of mass m1. It is swept along by a river, and and it depends on the speed v of the river. River is also moving with the speed v, acceleration due to gravity g, and density d of the boulder, means that stone. Now what you have to calculate the percentage change in maximum mass of the boulder that can be swept by the river when speed of the river increases by 1%. Okay. So please pause the video and try it yourself before jumping into the solution. Okay. So I hope you are done with the solution. So let's first decode the problem and then get into its solution. Okay, how we will solve it. So see, problem is very straightforward. We have a boulder. So boulder has a mass. It is not that ki river flow can carry any mass. So river flow can carry some limited mass. So maximum mass that can be swept by the river will depend on the velocity of the river speed, because fast moving river can swept away heavy masses also. Acceleration due to gravity and density of the boulder. So the mass of the boulder that river can swept away, it depends on the speed, density of the boulder, and the gravity. Now in the question it is given that let us suppose the speed of the river is increased by 1%. So definitely when speed will be increased, it can carry more mass, means it can carry away, sweep away more mass. So percentage change in maximum mass that can be swept away by the river, that you have to calculate. Okay. So definitely in the problem we don't know any formula, because for this type of problems we have not remembered any formula like F is equal to ma, yeah, work done is equal to force into displacement. So we have to derive a formula, and that using that formula we have to calculate the percentage change. So whenever in any problem you are stuck with the concept, means you don't know the formula, you derive it. So the best one of the best tricks to derive the formula is dimensional analysis. So if in the question it is given that mass is dependent on v g d, so we can write m is equal to k v x g y dz. Very straightforward. K is the constant. And now you just compare both dimensions. Dimension of LHS should be equal to the dimension of RHS. So what is the dimension of LHS? That is M. So M1, L0, T0. And what is V? V is the speed. So LT minus 1. So LT minus 1 x. Okay. And what is G? Acceleration. Acceleration is change in velocity upon time. That is LT minus 2. So LT minus 2 to the power of y. And what is D? D is the density, mass upon volume. So ml minus 3 to the power of z. You just group all the parameters like m, L, T, you group it and you compare the powers. So after grouping and comparing the powers, you get z to be 1, x plus y minus 3z is equal to 0, minus 2x minus 2y is equal to 0. On solving, you get x is equal to 6, y is equal to minus 3 and z is equal to 1. And definitely you just substitute the values and you get the you derive the equation. So see, this is the beauty, because see, every problems, if you talk about IIT JEE Advanced also, problems are very easy. It's just the approach. So now I hope you are getting the approach ki, you derive the formula. You should be proud of yourself ki you derived a very great formula. See how complex formula is this, ki k v की power of 6g minus 3d. So this is the relation between the mass which the river can sweep away and other parameters. Now using this relation, you have to calculate ki if speed of the river is increased by 1%, how much more mass it can carry away. So this is the next part. So let's look into it. Okay. So see, now here we have the mass. So now what we can do? We can calculate delta m upon delta v, means change in mass with respect to velocity. So differentiate mass with respect to v. So dm by dv we are doing. So when we do dm delta m by delta v, we get k. K is constant. V6 will become 6v5 and g minus 3d. So we are assuming g and d to be constant. So we get this k6v5g minus 3d. So delta m will be k6v5g minus 3d delta v, because we are taking delta v to the other side. Now we are dividing it with m. So delta m upon m is equal to, now in the right hand side instead of m we are putting the formula. So what is m? K v6g minus 3d. So that we can do. So that we are doing, and we do some cuttings. So k will cut and other parameters will cut. So finally we get delta m upon m is equal to 6 delta v upon v. Okay. Now in the problem, delta v upon v is given, because what is delta v upon v? Change in speed of the river. So change in speed of the river is 1%. So just substitute 1%. So delta m upon m we get. So what is delta m upon m? Change in mass. So change in mass will be 6%. So this is the answer. So if the speed is increased by 1%, the river can carry 6% more mass. So I hope this is clear. Okay. So now let's jump into the next problem. That is problem number 9. A massive object in space causes gravitational lensing. So gravitational lensing is a new concept for us. So let us see what is it is. Light from a distant source gets deflected by a massive lensing object. This was first observed in 1919 and supported Einstein's general theory of relativity. So the idea is this: कि, light from a distant source. So stars are emitting light, sun is emitting light. So from a distant source we are getting light. So that light is getting deflected. So deflection of light in itself is a very interesting concept by a massive lensing object. So this is known as gravitational lensing, and it was observed by supported by Einstein's general theory of relativity. So now let's see what exactly the question is. The angle theta by which light gets deflected due to a massive body. Okay, so angle of deflection, because light is deflected. So angle of deflection depends on mass of the body, definitely. Universal gravitational constant g, speed of light, that is a constant, and the least distance between the lensing object and the apparent path of the light. Okay, so dependency is given, the theta is dependent on all these things, you have to derive a formula for theta using methods of dimensions, make suitable assumptions. Okay, so definitely this is a very straightforward question, and I hope now you will be able to crack problems like this, because we have done lots of problems like this. So dependency is given, so just derive the formula. So I hope you will come up with a solution. So pause the video and try it yourself before jumping into the solution. Okay. So I hope you are done with the solution. So let's look into it. So definitely, so in such type of problems, what we can do, we can first to uh, establish a relationship, that is theta is proportional to g m speed c r, to g m c r. Okay, so this we can do. But here there is one more trick to make calculation easy. We are applying one trick. So the trick is this: see, theta is dimensionless, you know that. So LHS is dimensionless, so RHS should be also dimensionless, means all the dimensions should cut, means it should be reduced. So definitely, if I talk about simple observations indicate that mass is present in expression of G and M only. So if I talk about mass, so mass is not present in speed. C is the speed of light, and R, their mass is not present. Mass is present only in G and M. So we are grouping G and M together. So in this way, mass will cancel out. Means we can cancel out mass. So C and R will automatically get cancelled out. So what we have done, we have written theta is equal to k gm to the power of x, c to the power of y, and r to the power of z. So this you already know, we do like this. Now the next thing is to derive the dimensions of each and every quantity. So you know that gravitational constant. So you know the formula of gravity also, that acceleration due to gravity. Yeah, force of attraction, force of gravitational force is equal to capital G m1 m2 upon r square. From that you can very easily calculate capital G. So it will be m minus 1 L3 t minus 3. Okay. C is the speed. Speed is Lt minus 1. You know. M is mass, that is m1, and r. So what is r? R is the distance. So that will be L. So you just substitute the dimensions. So in the left hand side it will be m0, L0, t0, because it is dimensionless. In the right hand side we have this m minus 1 L3 t minus 3 C. So m minus 1 L3 t minus 3 multiplied by m. So m cancels out. It will get cancelled out. So we get L3 t minus 2 to the power of x, Lt minus 1 to the power of y, and L to the power of z. So after you just group all the quantities together and compare the powers. So you get 3x plus y plus z is equal to 0, 2x plus 2y is equal to 0. It implies that y is equal to minus x and z is equal to minus 2x. This you get, and yeah, now here you are not getting the exact value. So you are getting y is equal to minus x and z is equal to minus 2x. So you are not getting the exact value. So whenever you don't get the exact value, you have to make some suitable assumption. So let us assume x to be 1. So when you put x is equal to 1, you get y is equal to minus 1 and z is equal to minus 2, and just put it in the equation. So we get theta is equal to k gm upon cr square. Okay. Similarly, if we put x is equal to 2, we get theta is equal to k g2 m2 upon c to the power of 2 r to the power of 4. Uh, and the thing is this key, dimensionally this formula is correct, and dimensionally this formula is also correct. Okay, so dimensionally that formula was correct, this also. And if you put x is equal to 3, then also dimensionally you will get the formula to be correct. X is equal to 1 by 2, 1 by 3 you put, then also you will get the dimensionally the formula to be correct. So this is a drawback of the drawback if you are using dimensions to calculate the formulas, because you see that you can calculate multiple formulas. Definitely there cannot be multiple formula, there will be one formula, one relation, exact relation. So definitely, so that relation we calculated with some experiments. But definitely the dimensional analysis took us closer to the exact answer, because we got an understanding that gm upon cr square. Okay, so so the correct expression as calculated using experiment is theta is equal to k gm upon c square r. So this is the answer. Okay. Okay, so I hope this is also clear. So now let's jump into the next problem. So that is problem number 10. The Casimir effect describes the attraction between two unchanged conducting plates placed parallel to each other in vacuum. So plates, so we have two conducting plates. So they are placed parallel to each other. So when we place the plates, there is a special type of attraction between the two plates. So conducting plates. So that attraction is called Casimir effect. The astonishing force per unit area of each plate, because there is an attraction, so definitely both the plates will be experiencing a force. So the force per unit area of each plate depends on Planck's constant h, speed of light c, and separation between the plate. Okay, so the dependence of force is given on the some quantities. Using dimensional analysis, proved that the formula for Casimir force per unit area on the plates is given by this. So this you can very easily do. We have done lots of problem like this. If the force acting on 1 cross 1 centimeter plate separated by 1 micrometer is 0.013 dial, calculate the value of constant k. So once you have the formula, you just put the values in the formula, you get the value of k. So this is a, I think, easy problem. Easy because we have done lots of problem like this. So I think now you can crack this problem. So please pause the video and try it yourself before jumping into the solution. Okay, so I hope you are done with the problem. So let's look into its solution. So definitely it is given that force depends on H, C and R. So we can write F is equal to K, H, X, C, Y, R, Z. Very easy. Now we have to get the dimension of each and every quantity used. So F is the force per unit area. So F is not force, it is force per unit area. So dimension will be a bit different. So dimension will be, what is force? Force is mass into acceleration. So that is and L t minus 2 upon area. So what is area? L square. So the dimension will be m L minus 1 t minus 2 of LHS. And RHS, if you talk, so dimension of H, Planck's constant. So that is ml square t minus 1. So how? Because see, Planck's constant is energy upon frequency. So this you can very easily calculate Planck's constant dimension. Similarly, c is the velocity, speed of light. So speed is distance upon time. So lt minus 1 to the power of y. And what is r? R is the separation, that is distance, that is l to the power of z. You just group all the quantities m, l, t together, compare the powers, and you get x is equal to 1, 2x plus y plus z is equal to minus 1, minus x minus y is equal to minus 2. Solving, you get x is equal to 1, y is equal to 1, z is equal to minus 4. You just put x, y and z in the first equation. So we get f is equal to k h c r to the power of minus 4. So finally we get f is equal to k h c upon r to the power of 4. So this we prove. Now if we jump into the b part, it is very easy. So force per unit area is 0.013 dial. So Planck's constant value you should memorize, because it is a very important quantity used in many of the problems. So Planck's constant, speed of light, you already know. So see, speed of light is 3 into 10 to the power of 8. You got surprised ki how it is 3 into 10 to the power of 10, because it is centimeter per second. We are talking 3 into 10 to the power of 8 meter per second. But here we are taking everything in centimeter. So 3 into 10 to the power of 10 centimeter per second. R is given. What is R? As a separation. Separated by, so R is given to be 1 micrometer. So when you convert it into centimeter, it will get 10 to the power of minus 4 centimeter. So here you just put the values in the formula, so you get the answer. So basic calculation that you can practice and you can get the answer. So the value of k. Wonderful. So hopefully this is also done. So now let's jump into the next problem. So problem number 11. Scattering of light is a process of absorption and prompt re-emission of light by atoms and molecules. So definitely there are atoms and molecules everywhere. So whenever light passes through any object, scattering of light is a process which takes place. So what is scattering of light? It is absorption and re-emission of light by, so atoms and molecules first absorb light and they re-emit light. So that's why light gets scattered. Light gets scattered. Okay. Scattering involves particles smaller than wavelength of light is known as Rayleigh scattering. So definitely, there is an electromagnetic spectrum. So different waves are there. So light scattering involving particles smaller than wavelength of light is known as Rayleigh scattering. So if we talk about wave, we have X-rays. So that is also a special type of wave. We have gamma rays. So all of the different spectrum, that range has different wavelength and different frequency. So all the rays having wavelength smaller than the wavelength of light means visible light. So if those are involved, those rays are involved, then the scattering is Rayleigh scattering. It is given in the problem. Let AI be the amplitude of incident light on a scatterer of volume V. So amplitude, because for every wave there is an amplitude. So we have a scatterer of volume V. Sorry, light is hitting that scatterer and light of amplitude AI. The scattered amplitude at a distance r from the scatterer is As. Assume that As is directly proportional to AI. AI is the amplitude of incident light and As is the amplitude of the scattered light. You can assume that with the problem. As is directly proportional to 1 upon r and As is proportional to V. So in the problem, we have given relationship, some dependencies. Now what you have to find the dimensions of the proportionality constants according to the constant occurring in the expression of As. Okay, so see what you can do. See, you can write As is proportional to Ai into V upon R, because you can combine As is proportional to AI, As is proportional to 1 upon R and A is proportional to V. So when you combine, you get As is proportional to AI into V upon R. So when you remove that proportional, you get As is equal to K AI V upon R. So you have to find the dimension of K. Very easy. That I think you can do. And the second part is assuming that this constant depends on lambda. Find the dependence of ratio As upon AI on lambda. And the third part is knowing that the intensity of light is directly proportional to A square. Find dependence of Is upon II on lambda. So I hope you can do this problem. You have to just apply some common sense and logic. So please pause the video and try it yourself before jumping into the solution. Okay, so I hope you are done with the solution. You have the solution. So let's see. So as we have seen that As is proportional to VAIR. So As will be equal to KVAI. K into VAI upon R. So K will be, see, KV upon R is dimensionless. Okay, so there is a trick here, a very deep observation. So the deep observation is this: in the in the left hand side we have As. So As is amplitude, and in the right hand side also we have As, that is amplitude. Now both the dimensions should be same according to the principle of dimension. It means dimension of As will be equal to dimension of AI, because dimension of both the quantities are same, so their dimension will be same. So what trick we can do to make the calculation easy? It is from the observation we can conclude that k v upon r should be dimensionless, because if k v upon r is dimensionless, it will do the trick for us. So in order to be what is that dimension of v upon r? So v is velocity. Sorry, v is volume. So volume is L cube. Okay, and what is R? R is L. So L cube upon L is L square. So the dimension of V upon R is L square. So definitely the dimension of K should be L to the power of minus 2. So this is the trick. Okay. So see, it's all about your presence of mind. So here presence of mind played a role. It saved us from very troublesome calculation. So in 2 3 lines we got to the answer. So for presence, so you saw the importance of presence of time. So first part is done. So now let's jump into the second part. In the second part it is given, that assuming that this constant, that k, which we derived, it depends on lambda. So lambda is the wavelength. Find the dependence of ratio As upon Ai on lambda. So see, we know that the dimension of k is L minus 2. So if the dimension of k is L minus 2 and it is given that k is dependent on lambda, so definitely k should be proportional to lambda to the power of minus 2, because lambda is also length, wavelength is length. So the dimension of wavelength is also L. So we can write k is proportional to lambda minus 2. Now, so what we can write, uh, now you have to find the ratio. Now you have to find the ratio, what the ratio is, As upon Ai, that you have to find. So how you will find that As upon Ai? So that let's see how we will find. Okay. So As upon Ai. So see what we can do. We from the relation that As is equal to kVAI upon R. As upon Ai, we can say that it is proportional to k. So we can write k is proportional to As upon Ai. So k is proportional to As upon Ai, and k is also proportional to lambda to the power of minus 2. So automatically As upon Ai will be proportional to lambda minus 2. So this is the answer. So this I think you can get. Now let's move into the third part. So the third part is, now let's move into the third part. So the third part is knowing that intensity of light I is proportional to a square. Find the dependence of Is upon Ii on lambda. So we know that intensity is amplitude square. So that this we know. Okay. So Is upon Ii. So definitely Is is proportional to a square and Ii is proportional to ai square. So Is upon Ii will be proportional to As upon Ai square. And we know that As upon Ai is proportional to lambda, lambda to the power of minus 2, that we have derived. So very easily we can write As upon Ai ka whole square will be proportional to lambda minus 2 square. So it will become lambda minus 4. Okay. So I hope this problem is clear. Okay. So now let's jump into the next problem. So that is problem number 12. So in problem number 12, it is given that integral of dx upon 1 plus x square is equal to tan inverse x plus c. Using methods of dimension, find integral of dx upon a square plus x square. So see, by direct calculation, so you can very easily find the integral, but they are telling using methods of dimension, find the integral of dx upon a square plus x square. So please pause the video and try it yourself before jumping into the solution. Okay, so I hope you have solved the problem. So let's look how we can solve this integral using the concepts of dimensions, methods of dimensions. So denominator is a square plus x square. Okay. The integral which we have to find, its denominator is a square plus x square, which means that dimension of a should be equal to dimension of x, because we know that with the principle of dimensions, all the unit that terms dimension should be same. So a square plus x square means dimension of a should be equal to dimension of x. Also, the argument of tan inverse should be dimensionless, because the tan inverse definitely, or whatever argument we are passing, that should be dimensionless. So hence we can replace x by a, because x by a will also be dimensionless because both are having same dimension, so it will cut. So we can replace x to x by a. So with the principle of dimensions, we can say that this integral, the integral will be tan inverse x by a plus c. So therefore the integral can be written equal to a tan inverse x by a plus c. Okay. Yes. So now let's jump into the next problem. That is problem number 13. So this is an interesting problem. So let's see it. 2 point sources of light are fixed at the center A and circumference point B of a rotating turntable. So there is a rotating table. So at point A and at point B, we fix light sources. So light is emitting from there, and the table is rotating. A photograph of the rotating table is taken. So we took the photograph, the table is rotating. On the photograph, a point A and arc BC appears. So when you look into the photograph, you see that in the photograph we get a segment like the one with A, B, C arc. So we have a, in the photograph, an arc is there BC, and we got the point source A, light source A we got. Okay. The angle theta was measured in the photograph. We measured the angle theta to be 10.8 degree plus or minus 0.1 degree, and the angular speed of the turntable uh, was measured to be angular speed. Let us suppose it is omega. Omega is equal to 33.3 plus or minus 0.1. So it is revolution per minute. 33.3 plus or minus 1 plus minus 0.1 revolution per minute. It is given. Now what we have to calculate? We have to calculate the exposure time of the camera. So what is exposure time? Exposure time is uh, to how much time the camera took to click the picture. So that is the exposure time. Okay. So let's so please pause the video and try it yourself before jumping into the solution. Okay. So I hope you came up with the solution. So let's see. So let the exposure time be t, and the uncertainty, its value be delta t, because definitely there may be some uncertainty. So let the exposure time be t and uncertainty be delta t. Omega is given. So omega is 33.3 plus or minus 0.1. So we are taking omega to be 33.3, and it is revolution per minute. So revolution, let's convert it into angles, degrees. So one revolution is 360 degree. So instead of revolution, we can write 360 degree. And minute is, will we have to convert it into second. So upon 60. So 33.3 into 360 upon 60. So we get angular, angular speed is 200 degree per second. So every second the table is making an angle of 200 degree. So this is the angular speed. If you talk about time, so now the exposure time. So the exposure time is basically, you know that angular speed. What is angular speed? Angular speed, we can write angular distance upon time. So that is the angular speed. Because see, from a very deep observation, you can conclude that, you can observe that when you click the picture, sorry, so whatever arc is getting drawn, so the time taken to draw the arc is our exposure time. So that we can assume from the observation. So the time taken to draw the arc, or you can say that time taken to cover that distance. So you know that omega is equal to theta upon t, that angular speed is equal to angular displacement upon angular distance upon time. So time will be theta upon omega. So theta, I think it is given 10.8 and omega we just calculated 200. So time is 0.054 seconds. So this is the exposure time. So exposure time we have calculated. Now we have to calculate delta t. Now, see, in the problem, as you can see, for every that parameter, uncertainty was also given. But what we did, first we didn't consider the uncertain values. We just considered the original values and solved to get the original time. Now, what we will do, we will consider all the uncertain values to calculate the uncertainty in time, that is delta t. So definitely this relation you might know. If t is equal to theta upon omega, we can write delta t upon t is equal to delta theta upon that theta plus delta omega upon omega. So the idea is uncertainty in time is equal to uncertainty in your angular speed and uncertainty in your theta, that is that angular distance angle. So delta t will be t delta theta upon theta plus t delta omega upon omega. Okay. So yeah. So now what we can do, t upon delta theta we can write omega, 1 upon omega, sorry. So t upon delta theta we can write 1 upon omega. So it will become delta theta upon omega plus similarly t upon omega. So t upon omega. So t upon omega will also be 1 upon. So t upon omega we will keep it as it is. So it is delta omega t upon. Okay. So you can look very basic calculation. It is not just any new concept we are applying. So we are just solving it. So after putting all the uncertain values and the parameters, you get the delta t. So delta t is 0.003. So you get the final answer. So I hope this. So this is a very important problem because this kinds of question is usually asked. So I hope it is clear. Okay. So now let's look into the problem number 14. So it also it seems to be a very interesting problem. So let's look into it. The speed v of wave on surface of water is given by v is equal to under root of a lambda upon 2 pi plus 2 pi b upon delta that density. What we call it, rho, no? Rho lambda. Yeah. So this formula is given. The speed v of wave on surface of water. So definitely if we talk about moving water, so you have seen oceans. In ocean, yeah, sea, the moving water, it carries a wave. So the speed of wave is given. The formula for speed of wave is given, where lambda is wavelength of the wave and rho is the density of water. Small a is a constant and small b is a quantity. So small v is not a constant, it is a quantity that changes with liquid temperature. So definitely liquid temperature is here, it is water. Find the dimensional formula for A and B. So it seems to be easy. And sorry, B part is surface wave of wavelength. So wavelength is given 30 millimeter. Have a speed is given 0.24 meter per second. If the temperature of water changes by 50 degrees Celsius, the speed of waves for same wavelength changes to 0.23 meter per second. Okay, so initially we have a wave of speed this 0.24. When the temperature changes by 50, so let us suppose temperature is increased to 50, the wavelength, the speed changes to 0.23. So this is given, assuming that the density of water remains constant with temperature, that is density of water is given. Estimate the change in value of V for temperature change of 50 degrees Celsius. So it is a very interesting question. So please pause the video and try it yourself before jumping into the solution. Okay. So I hope you are done with the solution, done with the problem, you have got the solution. So let's look into the solution. So see, we have the formula, it is given. So if we square it out, so v square is equal to a lambda upon 2 pi plus 2 pi b upon rho lambda. Very straightforward observation. And we know that from the principle of dimensions, all the terms dimension should be equal. So dimension of v square should be equal to dimension of a lambda, because 2 pi is constant, should be equal to dimension of b upon rho lambda. Now v, what is v? V is velocity. So velocity is that LT, velocity is displacement upon time, LT minus 1. So m0 LT minus 1 to the power of 2 should be equal to a. So dimension of a into dimension of lambda. So the dimension of lambda is L. That should be equal to dimension of b upon rho. What is rho? Rho is density. So density is mass upon volume. So what is mass? Mass is m, and volume is L to the power of minus 3. So ml minus 3, and what is lambda? Lambda is L. Okay. Yes. So with very straightforward calculation, you get A is equal to m0 uh, L, because and t minus 2. This you can get. Similarly, B you get m L0 t minus 2. So I think these kinds of questions now you can very easily solve. So now let's jump into the B part, because B part is looking somewhat tricky. So let's look into the B part. Yeah. So in the B part, the question is very clear. Temperature is raised to 50 degree. Then definitely speed is decreased. Speed changes. So what we can do, we have the formula. This now using this formula, what we will put some values. So initial velocity we know 0.24. So 0.24 to the power of 2 is equal to a lambda 25 plus 2 pi b1. Let us suppose at that temperature the quantity is b1 upon density of water is given 10 to the power of 3, and wavelength is given. So wavelength is 30 nanometer, millimeter, sorry. So 30 into 10 to the power of minus 3. So if you do some basic simplification, so you get the first equation. Similarly, we get the second equation, that is we put v to be 0.23. So 0.23 square is equal to a lambda upon 2 pi plus that 2 pi b2 upon 30, because the wavelength will remain same. Now what we do 2 minus 1, because change. Okay, we are calculating the change. So we get when we do 2 minus 1, we get 0.23 square minus 0.24 square is equal to that a lambda 2 pi will cut. So we get 2 pi upon 30 b2 minus b1, this we get. Okay, and when you do some, so b2 minus b1 is delta b. So this you have to calculate, I guess. Yeah, you have to calculate this delta b. Okay, so delta b you can very easily calculate, very basic calculation, I hope you can do. So you got the, yeah, answer. So this is the final answer, which, because you have to calculate the delta b, so delta b we calculated. So uh, okay, so I hope you got the concept. Okay, then now let's look into the problem number 15. Yeah, so see, this problem is looking somewhat interesting. We have sun, earth, so I think it is a problem of astrophysics because we have solar system in this problem. So the line of sight of the brightest star in the sky. So we have a brightest star. The line of sight of the brightest star in the sky. The name of the star is Sirius. Has a maximum parallax angle of what you can call this constant. Let me call it delta only. Delta is equal to 0.74. So here that parallax angle is given, that is 0.74 plus minus 0.2 r second. So this angle is given when observed at 6-month interval. The distance between two positions of the Earth at 6 month interval is 3 into 10 to the power of 11 meter. Calculate the distance of Sirius from the Sun with uncertainty in unit of light year. So we have to calculate the distance in unit of light year with certainty. So we want exact answer. Given 1 light year is equal to 9.460 into 10 to the power of 15 meter. It is given. And pi is equal to 3.14. So let's try to decode the question because the question is a bit tricky. So see, from the question we can see that Earth is revolving around the Sun. So definitely at 2 points means in the interval of 6 months, Earth will be at two extreme positions, as you can very easily see from the figure. So the distance is r. So at the 6 month interval, the distance, that two extreme position distance is r. Okay, and when you measure the star, when you look into the star from these two extreme positions, you make an angle. That angle is given. That is, I think, this theta. Now using these parameters, you have to calculate the distance of the star from the sun. Now the problem is straightforward. So please pause the video and try it yourself before jumping into the solution. Okay. So now I hope you cracked the problem. So let's look into the solution. So the required distance, let us suppose it be x. So x will be r by 2 tan alpha by 2, because see, it will make a right angle triangle. Okay, so the perpendicular will be r by 2 and the base is x. Okay, and the that alpha, so here it is, they are using alpha. So let us suppose alpha will be alpha by 2 for the upper triangle. So you know that tan theta is perpendicular upon base, so tan alpha by 2 will be r by 2 upon x. So x will be r by 2 upon tan alpha by 2. So this is very clear. Okay. So it will be r by 2 upon. So tan alpha by 2 we can write alpha by 2 approximation. So it will be alpha by 2. So it will become r upon alpha. So x will be equal to r upon alpha. So alpha is given, that 0.74 arc second. So it is arc second. Okay. So we have to convert it into this radians. Yeah. So see, there is a trick. If you have to convert arc second into degree, you have to convert the that data by 3600. So for proof, definitely you can search Google. You can Google it out for the exact derivation, but it is a relation. So definitely, alpha is in arc second. We have to convert it into degree. So what we do, 0.74 upon 3600. I hope it is clear. So, and converting degree into radian is very easy. Multiply it by pi by 180. So we got the alpha in radians. Okay. So now x is equal to r upon alpha. R it is given. I think r is given in the problem. Yeah, 3 into 10 to the power of 11. So r is given meter, and 3 into 10 to the power of 11 r is given, divided by alpha we just calculated. So we get the x in meter, but you have to calculate the x in light year. So here definitely you should know the relationship between meter and light year. Okay, so what is light year? Okay, so here it is also given, 1 light year is equal to 9.46 into 10 to the power of minus 15 meter. So just convert, so just divide this by 9.46 into 10 to the power of minus 15. So definitely you will get the relation in light year. So when you solve it, you get the answer, that is 8.84 light year. It was a very nice question, I hope. So you can sorry, you can imagine कि astrophysics is bit difficult. You can see the calculation and all the geometry, trigonometry, application of concepts, conversions and all that. So being an astronomer is not easy. Yeah. So, okay, don't be happy. This was just the first part because we have to calculate the distance with uncertainty. So, we have calculated the exact distance. Now, let's calculate the uncertainty also. We know that x is equal to r upon alpha. We just derived. So, uncertainty in x is equal to r sorry r upon alpha square delta r. So this you might be knowing, you have already have studied this uncertainty concepts of uncertainty in units and dimensions chapter. So here uh, okay, because see in the problem uncertainty of angle is given. So uncertainty of r is not given. So that's why we just have to use the delta alpha. So delta x is equal to r upon alpha square delta alpha. So yes. So similarly, you can calculate delta alpha as we have calculated alpha. So delta alpha is 0.02 arc second. So divided by 3600 and multiply by pi by 180. So you get it in radians. So you just put the values, you get 0.24 light years. So this is the uncertainty. Now we have completed the problem. So true value we calculated and uncertainty also we calculated. Okay, so I hope you enjoyed this problem. Hello friends, welcome to this new video on problems in physics for IIT JEE Advanced Basic Mathematics Level 3. So definitely this is the third video. So level 1 and level 2 basic maths for IIT JEE Advanced Physics that I have already uploaded, so you can look into it. So today we will discuss on level 3. So definitely level 3 will be a bit more advanced questions, including bit more deep observation, thinking, intuition. So definitely it will be an exciting video. So I hope you will enjoy it a lot. Okay, so let's get started. Okay, so question 1. You inhale about 0.5 liter of air in each breath and breathe once in every 5 seconds. Okay, in question it is given that once every 5 seconds we breathe, and during each breath, that is inhale 0.5 liter of air, it is given. And it is also given that air, if we talk of air in totality, it has 1% of argon. So argon is a noble gas, you might know that. Mass of each particle can be assumed to be nearly 5 into 10 to the power of minus 26 kg. Atmosphere can be assumed to be around 20 kilometer thick, having a uniform density of 1.2 kilogram per meter cube. So definitely atmosphere, the thickness of atmosphere is given. So here thickness means, as you know that, see, Earth is a sphere, and definitely the atmosphere is also a bigger sphere surrounding the Earth. So thickness here, you can assume that the thickness is the height from the surface of the Earth to the to a particular height. So that height is 20 kilometer. So the idea is this: there is a concentric sphere. So the inner sphere is the Earth, and the outer bigger sphere is the atmosphere. And the difference of radius is 20 kilometer. So I hope this is clear that the meaning of thickness of atmosphere, and the density of atmosphere is given, that is 1.2 kilogram per meter cube. Okay, and it is also given that radius of the Earth is 6.4 into 10 to the power of 6 meter. It is also clear. Assume that when a person breathes, half of the argon atoms in each breath have never been in that person's lungs before. Okay, so it means they're trying to tell that, see, whenever we breathe, so definitely you can feel, you can observe that some particles are the particles which we breathed early. Because see, when we breathe, definitely many particles we breathe many times, because those particles are surrounded, means it is in our vicinity. So they are telling that we can assume that for every breath, 50% of argon, means half of the argon atoms are new. So they are trying to tell that in the question it is given that for every breath, 50% new argon atoms we inhale, and 50% means half of the argon atoms are those argon atoms which we have already breathed earlier. So it is given. So I hope this point is clear to you. This makes sense also. Argon atoms remain in atmosphere for long time. Why it is so? Because you know that argon is a noble gas. So noble gas does not react. So definitely argon remains in atmosphere for long time without reacting with any other substance. And it is also given that in 1 year we have 3.2 into 10 to the power of 7 seconds. It is given. So it is a very big question. Means, many scenarios are given. Once again, let's revise all the scenarios. Then let's come to the point ABC. Because see, this you should know that before jumping into the problem, first we should devote full time in understanding the problem. Because if you miss any point, you will make a mistake. So all your effort will get wasted. So uh, it is okay to devote some time in question, because understanding the problem is very important. So let's once again revise all the scenarios. Then let's jump into the exact problem which we have to solve. So see, in the question it is given that, see, we inhale, we breathe. So in the question it is given that we can suppose that we breathe for every 5 seconds. It means after 5 seconds, once again we do the inhaling and exhaling. So in the frequency of breathing is every 5 seconds we take the breath. It is given, and during the breathing we inhale zero point 0.5 liter of air. Okay, so this is very clear. It is also clear to us that during the breathing we inhale argon atoms also. So the argon atoms we inhale will be 50% new argon atoms, and 50% will be the argon atoms which are the old one. So that is also clear from the scenario. And it is also given that air has 1% of argon. Uh, and mass of each particle which we inhale is 5 into 10 to the power of minus 26 kilogram. If we talk about the atmosphere, the thickness of the atmosphere is 20 kilometer. We already know the meaning of thickness. And density of atmosphere is 1.2 kilogram per meter cube. Radius of the earth, which is a sphere, is given 6.4 into 10 to the power of 6 meter. And it is also given that 1 year is equal to 3.2 into 10 to the power of 7 seconds. Okay, so now let's jump into the exact problem which we have to solve. So the A part is estimate the number of argon atoms that passed through Newton's lungs in his 84 years of life. A very interesting question. So Newton, here you can assume Newton to be the scientist, Newton, the great Newton, or you can assume Newton to be any person. So the idea is this: कि Newton lived for 84 years. We have to calculate कि for 84 years how much argon atoms he inhaled. Very interesting question. Estimate the total number of argon atoms inhaled by the Newton in his 84 years of lifetime. So now from the scenarios, I think you can relate to the problem. Now B part, they are asking estimate the total number of argon atoms present in the Earth's atmosphere. Because in the question it is given that 1% or air has about 1% argon. So you have to calculate the number of argon atoms present in the Earth's atmosphere. So it is also a very interesting problem. Now let's look into the C part, what they are trying to ask. Assume that the argon atoms breathed by Newton is now mixed uniformly through the atmosphere. Estimate the number of argon atoms in each of your breath that were once in Newton's lungs? Very means interesting question this one is. So see, in this question they are telling, see, when we breathe, so definitely many argon particles will come out. We exhale many argon particles, and that will be spread around, dispersed in the surrounding. So definitely that organ atoms will be inhaled by other persons. So in this way, there will be a chain. You know corona, so you can very correlate this chain concept with the spread of the pandemic, that coronavirus spread. Okay, so they are trying to ask, uh, estimate the number of argon atoms in each of your breath that were once in Newton's lungs. So I hope the question is clear. Ki we have to calculate ki first we have to calculate ki how means whatever Newton has exhaled argon atoms. So when we inhale the air, how many of the argon atoms in the air which we inhale will be the argon atoms which were previously the part of Newton's lungs, means which went through the Newton's lungs. So the question makes sense. I request you to please pause the video and first try to understand the problem and all the scenarios, and please come up with the solution. First, you try it yourself before jumping into the solution. Yes. Okay. So I hope you are done with the solution. So it's see level 3 you can understand. So you can feel the quality, difficulty or quality of the problem of the level 3. So I hope you enjoyed the question. So let's try to solve one by one. So I hope the question is very clear to us. All the scenarios are clear to us. So in the A part, we have to calculate the number of argon atoms that pass through the Newton's lungs for 84 years. So see, let's do it with a proper approach. So we have to, in order to come to the final solution, we have to go step by step. We have to solve some small thing, and then definitely we will get to the final destination. That is the answer. So if you can imagine, see, for every breath, first let us calculate ki in every breath how many argon atoms we are inhaling, because see, ultimately we have to calculate ki how many argon atoms is inhaled by Newtons for 84 years. So first let's calculate ki for every breath how many argon atoms he inhaled. So once we know that, we can very easily calculate ki how many breath he has taken for 84 years, because see, for every 5 seconds there is one breath. So for 1 year, we can very easily calculate because number of seconds is given. So 5 into 3.2 into 10 to the power 7. So that is the number of breath in 1 year. And if we multiply by that 84, we get the number of breath in 84 years. And if we calculate the number of argon atoms in one breath, and we multiply it with that number, we get the answer. That is the total number of argon atoms inhaled by Newton during his 84 years of life. So I hope the approach is very clear. So let's means solve the problem. So definitely now we have to calculate ki during each breath how many argon atoms he inhaled. Okay, so that we have to calculate. So this is a very interesting part which we have to calculate. So let's see how we will calculate it. Okay. So first, let's calculate ki, how much means the mass of air inhaled by him, that in one breath, that we can calculate. Because see, if you look carefully in the question, you can see that volume is given. Volume of air is given, that is 0.5 liter, and density is also given. So density is atmosphere is density of air. So that is 1.2 into 1.2 kilogram per meter cube. So using these two parameters, we can calculate mass of air inhaled in each breath. So density is mass upon volume. So mass will be density into volume. So 0.5 liter we have converted into meter cube. So 0.5 into 10 to the power of minus 3 meter cube into 1.2. So when you do this, you get the mass. So we got the in each breath how mass of air inhaled that we got. Now mass of each particle is given. See, when you inhale, there will be lots of particles. So we have the mass of all those particles that we calculated. Now it is given the mass of one particle is given, that is 1.5 5 into 10 to the power of minus 26 kilogram. So if we divide the total mass inhaled by us upon mass of one particle, we get the total number of particles inhaled by Newton. It is very straightforward observation. I think you can very easily feel it. It is a basic observation. We inhaled lots of particles. So we know the combined mass. We calculated the combined mass. If I divide that combined mass with mass of one particle, I get total number of particles. So I got that. So I got the total. So these particles will be argon particles plus other particles also, because I calculated the total particles. Now I have to calculate the number of argon atoms, argon particles. So it is given that argon is 1% in air which we inhale. The that what you can say, the concentration of argon is 1%. So what you do, the total number of particles we calculated, we do the 1% of that, the 1 upon 100. We multiply it with that. We get the total number of argon atoms inhaled by Newton in one breath, each breath. So that is 1.2 into 10 to the power of 20. So I hope it is clear. Okay, but see, still we are not. This is not the final answer, because there is one more scenario to consider that we will look into. But until now, it is very clear. During each breath, 1.2 into 10 to the power of 20 argon particles is inhaled by Newton. But okay. Now here the trick is this, and see, total number of breath also we calculated. Now the trick is this, the other scenario which we have to consider in the question, it is given that during every breathing, 50% of the argon atom is the new, and 50% argon atom is the argon atom which he breathed earlier. It is not the new argon atom. So this is also clear, I hope. It is given in the scenario. So what we have to do, the total number of argon atoms inhaled by him, Newton. So we have to multiply it by 1 by 2. So that will be the total number of new argon atoms inhaled by Newton. I hope it is clear. So 1 by 2 into 1.2 into 10 to the power of 20 is the number of new argon particles inhaled by Newton in every breath. And if you multiply it with the total number of breath he did for 84 years, you get the answer. So after all the calculation, the final answer will be 3.2 into 10 to the power of 28. Okay. So I hope the this is very clear. All the approach and all the steps is clear. Yes. So now let's look into the B part. So if you look into the B part, what we have to calculate in the B part, total number of argon atoms present in Earth's atmosphere. Okay. So question seems to be very straightforward. We have atmosphere, 20 kilometer thick atmosphere. So total number of argon atoms, the total number of argon particles present in this atmosphere. This we have to calculate. So here also see what we know the density of air. Now definitely we have to start with the volume of atmosphere. So if I talk about volume, so volume, you know that volume is area into height. So here the scenario is this: we have a sphere. So that sphere is Earth. So Earth is a sphere. So from the surface of the Earth, we take 20 kilometer and draw one more sphere. So this region, the region of 20 kilometer, that segment. So that is the volume which we have to calculate. So we have two sphere, the bigger sphere and the inner sphere. Inner sphere is the Earth, the bigger sphere is the atmosphere. So the segment the segment between the Earth and the outer segment, that outer atmosphere. So that volume we have to calculate. So that is the volume of the atmosphere, and the thickness is 20 kilometer. Very straightforward observation that you can do. So there are two ways to calculate it. The first one is you calculate the volume of outer sphere, you calculate the volume of inner sphere, and you do the minus. Means from outer sphere take out the inner sphere. So the remaining that material, the volume is the volume of the atmosphere. But this is a lengthy process because r cube 4 by 3 pi r cube you have to calculate. It will take lots of time to be very precise. So see, in competitive exams, it is not just about solving problem, but it is solving problem quickly, because you have to solve lots of problems. So the easy method will be calculate the curved surface area of the earth, because it is a sphere. So very easy. This you have studied in class 10th also. The curved surface area of the sphere is 4 pi r square, and multiply it with h. H is the thickness of the that your atmosphere. So you get that volume. So this is a easy calculation because just 4 pi r square into h. So you will save lots of time with this. Okay. So now we can very easily calculate the volume of the atmosphere. We have estimated that half a liter, so half a liter air has 1.2 into 10 to the power of 20 argon atoms. So this we already have done. If we talk about half liter air, which the Newton inhaled, so in that half liter air, the number of argon atoms is 1.2 into 10 to the power of 20. So definitely, if you know the number of argon atoms in half liter, so definitely you can very easily calculate the number of argon atoms in the volume which we just calculated. So, so number of argon atoms in 1 liter will be 1.2 into 10 to the power of 20 upon zero point 0.5 into 10 to the power of minus 3. This is basically a unitary method which we have studied in class 9th. And if we have to calculate the number of argon atoms in volume 4 pi r square h, so what we have to do, we have to just multiply. So 1.2 into 10 to the power of 20 upon zero point 0.5 into 10 to the power of 3 into 4 pi r square h. So I hope this is also clear. So once again, let's see it. See, we inhaled half liter that air. So that half liter air contained 1.2 into 10 to the power of 20 argon atom. So half liter contains this many argon atom. 1 liter will contain 1.2 into 10 to the power of 20 upon half. That is 0.5 into 10 to the power of minus. This is the number of argon atoms in 1 liter, and number of argon atoms in 4 pi r square h will be the number of particles we calculated just now into 4 pi r square h. So you get the number of particles, argon atoms in the total volume of the atmosphere. So after solving, you get the answer to be 2.5 into 10 to the power of 42. Okay, so let's jump into the C part. So in C part, what they are asking. So assume that the argon atoms breathed by Newton is now mixed uniformly through the atmosphere. Estimate the number of argon atoms in each of your breath that were once in Newton's lungs. Definitely, when Newton will do breathing, many of the argon atoms he exhale will be dispersed, and that same argon atom you will inhale. So you have to estimate the number of argon atoms in each of your breath, that half liter you breathe. So in that half liter, how many argon atoms were the part of Newton's lungs? I think the question is clear. So if you are facing difficulty in understanding the question, I request you to pause this video and devote some time. Read it 10 times. Try to observe. Try to decode. Because see, physics is all about observation. Deep observation will only help you in solving the problems. It's not about ratification. If you talk about competitive program, sorry, not program, competitive exams, I hope you're getting what I'm trying to tell you. So this is a very interesting question. Let's decode it. How we will do it. So see, the two observations we have to make. The first observation is means see when Newton inhales, so definitely he inhaled half liter of air. So in that half liter, how many new argon atoms he inhaled? That we have already calculated. During every breath by Newton, how many new argon atoms inhaled by him? So that we calculated in the first part, as you can see, that is 3.2 into 10 to the power of 28. So this we have calculated. So now ultimately these new particles of argon atoms inhaled by Newton will be exhaled by him. So for every breath, 3.2 into 10 to the power of 28 argon atoms are introduced in the atmosphere. So these argon atoms are special argon atoms coming from Newton's lungs. So we can consider that atmosphere to be a system. So in this system, for every breath, 3.2 into 10 to the power of 28 new argon atoms are getting introduced, special argon atoms are getting introduced belonging to Newton's lungs. This observation is very clear, very simple, very straightforward. We have already done the calculation. And in the system, in the atmosphere, we have calculated the total number of argon atoms. That is 2.5 into 10 to the power of 42. So these two observations we have already done. Now, if I have to calculate the fraction of special argon atoms belonging to Newton's lung in the atmosphere, so fraction means out of the total, how much? So that is fraction. So the total is 2.5 into 10 to the power of 42, and the special is 3.2 into 10 to the power of 28. So if you divide 3.2 into 10 to the power of 28 upon 2.5 into 10 to the power of 42, you get the fraction of argon in atmosphere belonging to Newton's lungs. This is very clear. So that fraction is 1.3 into 10 to the power of minus 14. Now exactly I have to calculate it during my every breath. Exactly means how much particles of Newton means out of 1.3 into 10 to the power of minus 14 means how much particles I will inhale that belong to Newton's lungs. So 1.3 into 10 to the power minus 14 is the fraction. 1.3 into 10 to the minus 14 is the fraction. Exactly the number of special atoms in the atmosphere that visited Newton's lungs is 3.2 into 10 to the power of 28. This is clear. So 3 point, so out of 3.2 into 10 to the power of 28 special argon atoms, how many argon atoms I will inhale? That I have to calculate. Okay, so let's see how we will calculate that. So see here there is a trick. So this trick you have to remember, and definitely I will suggest you to give time and do some research from your side to get the exact understanding of this trick why this is so. So the trick is this. See, when I will inhale half liter of air, I have calculated the total number of argon atoms inhaled by me. That I have calculated. That is 1.2 into 10 to the power of 20. So during my every breathing inhale, I will inhale 1.2 into 10 to the power of 20 argon atoms. This is this observation we have done. Now out of this, what it is out of this 1.2 into 10 to the power of 20 argon atoms, what I will do, I will assume that the fraction of special argon atoms belonging to Newton's lungs is 1.3 into 10 to the power of minus 14. So I multiply both. So with this, I will get the number of argon atoms inhaled by me number of special argon atoms inhaled by me belonging to Newton's lungs. So see, I inhaled air, I inhaled argon atoms. So I inhaled lots of argon atoms. So definitely in those lots of argon atoms, there are some special argon atoms belonging to Newton's lungs. So that also I inhaled. So how you will get that? Fraction of special argon atoms in the atmosphere multiplied by total number of argon atoms inhaled by you. If you do this, you get the required number of special argon atoms inhaled by you, which belong to Newton's length. So that is 1.5 into 10 to the power of 6. So see, these are the standard questions requiring a very deep observation, very deep intuition, and very solid understanding of concepts. Okay, so and the beauty of all these questions, all the three questions you have seen is just 3 4 lines. So I have already in the previous lectures also I have discussed with you. In competitive programming, all the whatever may be the question, uh, the solution you get in a very limited number of lines. So if you are taking lots of time and if you are doing lots of calculation, it means your approach is wrong. So you have to definitely work on that. So see, with just 2 3 lines, the previous question was also just 2 3 lines, and this is also just 2 3 lines. Have very means basic steps you have to follow to get to the answer. So I hope this is also clear. So now let's jump into the next question. That is question number 2. So in question number 2, a rope is tightly wound along the equator of a large sphere of radius r. So we have a rope of unknown length. So we just wound it around the equator of a sphere. So you can imagine a sphere, and we just wound it to any surface of the sphere. The length of the rope is increased by a small amount L. So definitely we increase the length of the rope by a very small amount L, and it is pulled away from the surface at a point to make it taut. So definitely when we increase the length of the rope will get loose. So, so when we will pull it up, so it will get plugged out the rope, because you can imagine there is a surface, there is a rope. When you pull out, as you can see in the diagram, so you get a height. So there is a height which we get. So you have to calculate that height. So some parameters are given. Radius of Earth is given 6400 kilometer. Length is given. So the original length is unknown, but it is given that we increase the length by 10 millimeter. So that is given. We have to find the value of h, and you also have to make some assumption for small theta, because here we can assume the angle is small. For tan theta you can write theta plus theta 3 by 3. This assumption you can make, and for sec theta you can make 1 plus theta square by 2, and also take 2 by 3 to the power of 2 upon 3 is equal to 1.74. So these assumptions you have to make. So I hope the problem is clear. So please pause the video and try it yourself before jumping into the solution. Okay, so I hope you came up with the solution. So it's a very interesting problem. So this problem requires some very deep observation and a very interesting trick, which will help you in getting rid of some very complex calculations. See, tricks helps you, yeah, observation helps you in getting rid of calculations. So that is for smart work. So definitely we should practice ourselves uh, to such an extent that for every problem we do the smart work. So see, uh, if we talk about this diagram, so we can draw it like this. So we have a sphere, we have endpoints A and C. So we can assume that from A to C, a length of a rope of unknown length, it's touching the surface. Now we pluck it out because we increase the length by L, and we pluck it out, means we lift it out. So it will reach a point P. So we have a point PB. So PB is H and OB is R, that is radius. OA is also R and OC is also R. So triangle APO, and triangle APO is a right angle triangle. Angle POC is also a right angle triangle. So from this diagram, we can very easily derive H. So let's try to decode that. Okay. Okay. So see, we can make an assumption that we are pulling up the rope from the center. This we can assume to make our calculation very easy and very systematic. So we are pulling up the rope by the center. So if I talk about AP, because if I get AP, then I can definitely get to theta and then H. Ultimately, in this problem, our goal is to find small h, and we have to find small h. So first we are starting with AP. So if I talk about length of AP, so AP is the extended thread. See, we have AB. So AB is that the length, the rope of unknown length. So half of rope of unknown length, that is AB. And when we increase the length, we get AP. So from the very deep intuition, observation also, you can say that length of AP is equal to original length, that is length of arc AB, arc AB plus L by 2, because see L is the new addition to the length. So L is the new addition to the length. So definitely this region, this AB region will get L by 2 addition, and BC region will get L by 2 addition. I think this you can very easily feel. Very deep observation. We have a length AC. We are calculating from the midpoint, observing from the midpoint. When we increase the length by L, so this segment, that AB segment, as you can see here, this AB segment, this will get L by 2 increase, and this BC segment will also get L by 2 increase. So if I talk about AP is equal to original length, that is length of arc AB plus L by 2, and theta is equal to arc upon radius. So length of so theta is equal to arc upon radius. So arc will be theta into radius. So arc AB will be theta r, or r theta. So we can write r theta plus L by 2. We can write r theta plus L by 2. And what is AP? Because see, it is a right angle triangle, so you can apply trigonometry. Sorry. So trigonometry, you know that tan theta is equal to perpendicular upon base. So very easily you can look into that. AP is r tan theta. So r tan theta is equal to r theta plus L by 2. In the question, it is given tan theta is equal to theta plus theta 3 theta to the power of 3 by 3. So that we can substitute. So r theta plus theta to the power of 3 upon 3 is approximately equal to r theta plus L by 2. After solving, you get this, and finally you get theta. So theta is 3L upon 2r to the power of 1 by 3. So this you get. So theta we calculated, but ultimately we have to calculate small h. So see, we got the theta. We have to calculate small h. So now let us consider this OP. So if you look this OP is R plus H. Okay, R plus H, and definitely in the triangle OP is R sec theta. So that very basic trigonometry you can very easily calculate. OP is R sec theta. So we can write R plus H is equal to R sec theta, and instead of sec theta we can write 1 plus theta squared by 2. So it will become R plus H is equal to R 1 plus theta squared by 2, and after solving you get H, and instead of theta you can substitute. So you get the formula. These kinds of problem are very important in terms of your competitive, especially the JEE Advanced. So see, just within 1 minute you can solve it. So easy. Looking at it, it was looking very difficult, but with right approach, with smart, as I am telling smart work, we got H, knowledge we derived. So here the magic was in this observation. Because if you don't do this observation, then you will be filling up pages and pages and pages to get to the answer. And with just one observation, deep observation, this is a very deep observation. I hope you got the observation. We reduce the problem. So there are, to get to the solution, we can follow many paths. So we have to practice ourselves to always follow the shortest path. Okay. So now what we can do? We can substitute the values to get the H. So R we have derived. So it is given. R is given. L is given. So if you put the values and you get the this 5.6 meter. So here one more interesting thing you can see that if we talk about Earth, so in the Earth we have a large rope of unknown length, and if we increase the length of the rope by just 10 millimeter, and if we try to pull it out, so the height to up to which we can pull it out is 5.6 meter. So 5.6 meter is a very significant height. We can very easily watch it with just 10 millimeter of expansion of length. We get 5.6 meter. So this is a very interesting observation. So I request you to please dig deep into it and try to feel it. Ki how is it possible ki with just 10 millimeter of increase in length, how it is, how we are able to pluck it out of 5.6 meter. So I hope it is clear. Yes. Okay. Okay, friends. So we are done with the level 3 of basic mathematics for this IIT JEE Advanced Physics. So basic math series is completed. So level 1, level 2, level 3 is completed. And what I will do, I will make one video in which I will compile all the levels into a single video, and that also I will upload. So that also you can refer, so that all the question in one place. So we are done with this. So next, our next target is kinematics. So kinematics also level 1, level 2, level 3. So kinematics will be having lots and lots of, we will be solving hundreds of questions of standard questions. So I hope you enjoyed watching this video, and definitely you got some great ideas how to solve problems, approach, smart work and all that. And I request you to practice lots of problems, because as you know that solving problems will help you in getting a good mark and a good rank in exams. Because ultimately you have to become problem solver. Because when you become engineer also, you will be solving lots and lots of real world problems. So from this point onwards, you have to practice yourself. You have to solve problems. Because if you join a big company also, you will be solving problems. You will be get paid for your problem solving ability. So definitely you have to work on that problem solving. Thanks for your time. Thanks for watching. Stay tuned and subscribe to my YouTube channel and